July 21, 1937, Springfield, Massachusetts. Inside a brick arsenal building that's been manufacturing weapons since George Washington ordered its construction, a quiet Canadian-born engineer named John Garand watches a foreman load 8 cartridges into a metal clip. The foreman slides the clip into a rifle receiver, pulls back the operating rod, and steps away. Garand himself lifts the weapon, shoulders it, and fires a single shot into a sandbank 30 feet away. The rifle cycles smoothly. The bolt strips the next round from the clip. He fires again, and again. 8 shots in rapid succession, each one ejecting a spent casing while feeding a fresh cartridge. When the 8th round fires, the empty clip ejects with a distinctive metallic ping. The bolt locks open. This is the first production model M1 rifle to pass proof firing, function firing, and accuracy testing, the weapon that will arm every American infantry soldier in the coming global war. The rifle General George Patton will call the greatest battle implement ever devised. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But here's what nobody at Springfield Armory believes on this summer morning in 1937. This rifle cannot be mass-produced. The breech mechanism is too complicated, the tolerances too tight, the gas operating system too delicate. Even Springfield's own industrial personnel, the men who've been manufacturing weapons for 140 years, insist it's impossible to fabricate in large quantities. They're building 10 rifles per day, and they consider that an achievement. Garand says nothing. He's spent 18 years designing this weapon. He knows exactly how it will be manufactured at scale because he's already designed most of the tooling himself. What happens next transforms not just how America arms its soldiers, but how the world thinks about precision manufacturing under impossible deadlines. By January 1944, Springfield Armory will produce 164 M1 rifles every single hour, not every day, not every shift, every hour. One rifle rolls off the line every 90 seconds, 24 hours per day, 7 days per week. A weapon with 63 individual parts, each machined to tolerances measured in thousandths of an inch, assembled faster than most factories can stamp out sheet metal. The story of how this happens reveals a profound truth about industrial warfare. Technical brilliance means nothing if you can't build it fast enough. And building it fast enough requires destroying every assumption your experts hold about what's possible. November 1899. A textile mill in Jewett City, Connecticut. 11-year-old John Garand, fresh from Quebec after his mother's death, learns his first lesson in American manufacturing. He sweeps floors around massive looms powered by overhead line shafts, leather belts transferring power from a central steam engine to dozens of machines simultaneously. The noise is overwhelming, the machinery hypnotic. While other boys daydream about escape, young Garand studies the mechanisms. How do the cams transfer motion? Why do certain gears mesh while others slip? What makes one leather belt last longer than another? By age 12, he's operating machinery. By 16, he's fixing it. By 18, he's improving it, redesigning cam profiles and gear ratios in his spare time. He patents his first invention before his 19th birthday, an automatic bobbin winding machine that does the work of 3 skilled operators. The textile mill owners ignore it. They prefer craft tradition over mechanical efficiency. Garand files the patent anyway and moves on. He finds work at Brown and Sharp in Providence, Rhode Island, one of America's premier precision tool-making firms. Here, he learns something more valuable than textile mechanics. He learns how to measure in 10,000ths of an inch, how to grind cutting tools that maintain accuracy through thousands of operations, how to design fixtures that hold workpieces identically, cut after cut, hour after hour, with zero variation. These are not rifle-making skills, they're tool-making skills. But they're exactly the skills required to mass-produce rifles that everyone says can't be mass-produced. In 1917, the United States enters World War I completely unprepared. The Army possesses roughly 100,000 Springfield Model 1903 bolt-action rifles. They need millions, Springfield Armory, the nation's primary weapons manufacturer, promises to ramp up production immediately. They fail spectacularly. The armory manages to build 265,620 rifles during the entire war, a respectable number by peacetime standards but pathetically inadequate for modern industrial conflict. The embarrassment runs deep. America, the nation that invented interchangeable parts and assembly line production, cannot arm its own soldiers at scale. The War Department begins searching for civilian engineers who understand both weapons and manufacturing. Someone mentions John Garand, the toolmaker from Providence who's been designing an experimental light machine gun. They offer him a position at the Bureau of Standards in Washington. Then, in 1919, they transfer him to Springfield Armory with a clear directive. Design a semi-automatic rifle that can replace the model 1903. Make it reliable. Make it accurate. And for God's sake, make it manufacturable. Garand arrives at Springfield Armory and immediately recognizes the problem. The facility isn't designed for modern production. It's designed for craft manufacturing, the same approach that failed so catastrophically during the war. Individual machinists work individual machines, making individual parts that skilled assemblers then hand-fit together. Each rifle is technically interchangeable, but each rifle also requires hours of skilled fitting and adjustment. This approach worked in 1890. It barely worked in 1917. It won't work at all in the next war. Garand starts with the rifle design itself. Most semi-automatic rifles of the era use primer-actuated or recoil operation, mechanisms that require numerous small parts working in precise timing. Garand chooses gas operation, a long-stroke piston system that uses expanding propellant gases to cycle the action. It's mechanically simpler, fewer parts, larger tolerances, more forgiving of dirt and mud. The initial prototypes use a unique primer-actuated system. They failed testing in 1924. He redesigns completely, switching to gas operation, new prototype, new testing, new failures. The gas system creates excessive fouling. He redesigns the gas port location and size. The military wants .276 caliber. He designs in .276. Then, in February 1932, the Army Ordnance Department abruptly changes its mind. All development in .276 caliber will cease immediately. Everything must convert to the standard .3006 cartridge because the military has millions of rounds in storage and refuses to obsolete them. Garand starts over, completely. A new receiver design for the larger cartridge, new bolt, new operating rod, new gas system calibrated for different pressures. He's 44 years old. He's spent 13 years on this project, and he's back to preliminary designs. Lesser men would quit. Garand files new patents and keeps working. By August 1933, his .3006 design, designated T1E2, becomes officially designated as the United States Semi-Automatic Rifle, caliber 30, M1. But designation isn't adoption. The rifle must survive field trials. 75 prototypes go to infantry and cavalry units in May 1934. The reports that come back are brutal. The rifles malfunction in dust. The gas system fouls after 200 rounds. The operating rod bends under sustained fire. Garand incorporates fixes: enlarged gas port, strengthened operating rod, improved gas trap design. New trials in 1935. More problems, more fixes. Finally, on November 7, 1935, the rifle clears procurement. On January 9, 1936, it's officially standardized as the M1, and then comes the real challenge. The Army wants 65,000 rifles for initial issue. Springfield Armory's production managers look at Garand's drawings and panic. The receiver alone requires 97 separate machining operations. The bolt needs 53. The operating rod, the gas cylinder, the barrel, each one demands precision work on specialized equipment the Armory doesn't own. The tooling must be designed from scratch. Dies, jigs, fixtures, gauges, cutting tools, inspection equipment, all custom-engineered for this specific rifle. Traditional manufacturers would contract this work to outside firms, spending years in development. Garand designs most of it himself, working 16-hour days in Springfield's experimental shop. He understands something the production managers don't. Tooling determines speed. If you design the tools correctly, unskilled operators can produce precision parts at high volume. If you design them incorrectly, even skilled machinists will struggle. By July 1937, when that first rifle passes testing, Garand has already designed 80% of the production tooling required. Springfield begins manufacturing at the only pace they can achieve. 10 rifles per day, 1 rifle every 48 minutes, assuming everything works perfectly. It never works perfectly. Real production averages 8 rifles per day. The Army does math and realizes that at this rate, equipping 200,000 infantrymen will take 68 years. They authorize facility expansion. By January 1940, Springfield Armory produces 100 rifles per day. This represents a 10-fold increase in 18 months, and everyone involved considers it remarkable. They're manufacturing 500 rifles per week, 2,600 per month, 30,000 per year. Then, Europe explodes. France falls in 6 weeks. Britain stands alone. And suddenly 30,000 rifles per year looks like a sick joke. The War Department starts making phone calls. October 1940. Springfield Armory breaks ground on Building 104, a purpose-built facility designed specifically for high-volume M1 production. The project cost $3 million, roughly $55 million in 2025 currency. The timeline: 4 months from groundbreaking to operational production. Traditional military construction takes years. This building must be functional by February 1941. The pressure isn't theoretical. German submarines are sinking British supply convoys faster than Britain can replace them. Japan is systematically conquering China. The Soviet Union has signed a non-aggression pact with Nazi Germany. America isn't in the war yet, but everyone with a pulse knows it's coming. Building 104 rises through November and December, steel framework going up through Massachusetts snowstorms, while electricians wire panels and machine tool installers position equipment before the walls are complete. The building measures 600 feet long, 200 feet wide, not massive by automotive standards, but enormous for a firearms plant. What makes it revolutionary isn't size, it's organization. Traditional armory buildings concentrate machinery by type. All drill presses in one area, all milling machines in another, all lathes in a third. Parts move from building to building, floor to floor, often waiting hours or days between operations. Building 104 organizes by product flow. Receiver blanks enter one end, finished rifles exit the other. Every operation required to transform raw steel into a functioning firearm happens in sequence along a single path. This is automotive thinking applied to weapons manufacturing. The Ford River Rouge plant had pioneered this approach for Model T production in the 1920s. Willow Run would perfect it for B-24 bombers in 1942, but in 1941, applying assembly line logic to precision firearms still strikes most experts as lunacy. Rifles aren't cars. Tolerances matter. Each part must fit precisely or the weapon malfunctions. How do you achieve precision at automotive speed? Garand's answer is elegant. You don't fit parts to individual rifles. You fit parts to specifications so tight that any part fits any rifle. This is interchangeable parts manufacturing, the American system that Springfield helped pioneer during the Civil War. But Garand pushes it further. He doesn't just want interchangeable parts. He wants parts machined to identical dimensions with zero skilled fitting required. This demands tooling designed around absolute consistency. His receiver jigs don't just hold the workpiece. They position it identically, every time, within 5/10,000ths of an inch. His drill guides don't just locate holes. They prevent drill drift through hardened bushings that maintain alignment through 10,000 operations. His gauges don't measure. They go or no go, allowing workers to verify parts instantly without micrometers or mathematical calculations. A minimum wage worker who's never seen a rifle can learn to operate Garand's fixtures in 3 days. Not because the work is simple, because the tooling is brilliant. Building 104 becomes operational in February 1941. Initial production reaches 200 rifles per 8-hour shift, 160 per day when running 2 shifts. The armory production managers finally start believing this might actually work. Then Pearl Harbor happens. December 7th, 1941. Japanese bombs turn the Pacific Fleet into scrap metal. President Roosevelt addresses Congress the next day. America is at war, and the Army needs rifles. Immediately. Not next year, not next month, now. Springfield Armory goes to 3 shifts, 24 hours per day, 7 days per week. Production surges to 600 rifles per day by January 1942. Then 1,000 per day. Then 1,100 per day. The pace is staggering. Workers arrive for 6 a.m. shift and find the previous shift's rifles already packed in crates, ready for shipping to training camps where recruits are waiting. Some of those recruits will carry these rifles into combat within 6 months. The human cost of this acceleration needs acknowledging. Workers are pulling 10-hour shifts, 6 days per week. Women comprise 43% of the workforce by 1942. Many of them wives or mothers of men already fighting overseas. They're operating heavy forging hammers, running multiple drill presses simultaneously, lifting components that weigh 40 pounds. Safety protocols exist, but production pressure overrides caution. Fingers get crushed in presses. Burns from forging operations send workers to first aid stations. The noise level causes permanent hearing damage. Nobody complains. Or rather, everyone complains constantly, but nobody stops working because they understand what's at stake. Every rifle that doesn't roll off the line today is a rifle some soldier won't have tomorrow when he hits a beach in the Pacific or drops into France. By January 1943, Springfield produces over 3,000 rifles per day. This requires precision orchestration. Raw steel arrives by rail every 6 hours. Barrel blanks come from outside contractors already rough machined. Stock blanks arrive from lumber mills pre-cut to approximate dimensions. Everything must arrive exactly when needed because there's no storage space for inventory. Building 104 runs on just-in-time delivery before Toyota makes the concept famous. The receiver manufacturing process illustrates the systematic brilliance. Raw steel enters as rectangular forgings, heated to orange heat in gas furnaces, then hammered in massive drop forges that pound them into rough receiver shape. Still glowing, they go directly to heat treatment, quenched in oil baths that harden the steel to Rockwell C38. This hardness is critical. Too soft, and the receiver will wear rapidly. Too hard, and it becomes brittle, prone to cracking. The quenching process requires precise temperature control and timing. Variance of 50 degrees Fahrenheit ruins the batch. From heat treatment, hardened receivers move to rough machining. This is where Garand's tooling genius becomes apparent. Traditional machining requires skilled operators who measure, adjust, and verify each cut. Garand's fixtures eliminate measurement. The receiver drops into a jig that positions it identically to every previous receiver. Drill guides pre-positioned at exact locations. Cutting tools pre-set to exact depths. The operator's job is mechanical, not intellectual. Insert part, activate machine, remove part, inspect with go-no-go gauge. If the gauge says good, the part is good. No mathematical calculations, no micrometer readings, no judgment calls. A worker who couldn't solve a basic algebra problem becomes capable of producing precision parts because the intelligence is built into the tooling. Receivers go through 97 separate operations, but they flow continuously. Each machine is positioned within 15 feet of the previous operation. No waiting, no queue. As soon as Operation 47 completes, the part moves to Operation 48. By Operation 97, a hardened steel forging has become a finished receiver with exactly 33 holes drilled at precisely specified locations, every internal surface milled to exact dimensions, every critical dimension verified by dedicated gauges. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Total elapsed time from forging to finished receiver, 48 minutes. No skilled fitting, no handwork. Pure systematic manufacturing. Barrel production runs parallel on dedicated equipment. Barrel blanks arrive already rifle bored and chambered by specialty contractors. Springfield's job is final operations. Each barrel gets threaded for the receiver, crowned at the muzzle, drilled for the gas port, and proof tested. The gas port location is critical. Too close to the chamber and gas pressure is too high, battering the operating rod. Too far toward the muzzle and pressure is too low, causing failures to cycle. Garand calculated the optimal location through hundreds of test firings. His production drawings specify the distance to 5/1000ths of an inch. The drill jigs maintain this tolerance through 10,000 barrels. Stock production uses technology from 1819. Thomas Blanchard invented the first profile lathe at Springfield Armory, a device that could duplicate irregular three-dimensional shapes by tracing a master pattern while cutting tools reproduced the shape in wood. By 1943, Springfield operates advanced Blanchard lathes capable of cutting 3 stocks simultaneously, exterior shaping and sanding completed in 12 minutes. Interior inletting requires milling operations to create the precise voids that clear the barrel and receiver. These cavities must be exact. The barrel channel in particular, if too tight, the barrel binds and accuracy suffers. If too loose, the barrel shifts during firing and accuracy again suffers. Acceptable tolerance, plus or minus 0.08 of an inch over a 20-inch length. Automated milling equipment achieves this, stocks moving through a sequence of cutting operations on powered conveyors, while operators monitor for tool wear and replace cutters on schedule. By January 1944, Springfield hits peak production. The numbers are staggering. 122,001 rifles produced that month. Over 3,936 rifles per day, 164 rifles per hour when running 3 shifts. 24/7 production. 1 rifle every 90 seconds, let that penetrate. Every minute and a half, a completed M1 rifle, all 63 parts machined, heat-treated, assembled, and function-tested, rolls off the Springfield production system. This isn't automotive production applied to rifles. This is a new category of manufacturing, precision mass production, where tolerances measured in thousandths of an inch meet output speeds measured in seconds. The quality control system is as sophisticated as the manufacturing system. Every rifle receives multiple inspections. Receivers are gauged after heat treatment to verify hardness. Critical dimensions checked with dedicated fixtures. Barrels proof-fired with overpressure ammunition to verify they can withstand combat stress. Completed rifles function tested by cycling dummy ammunition through the action. Any malfunction equals rejection. No second chances, no adjustments. The rifle either works perfectly or goes back for rework. Approximately 15% of rifles fail initial inspection. Most failures are minor. A burr on the operating rod slot. A gas port drilled 0.002 inches off specification. An ejector that's slightly too short. Workers at the rework station, typically the most experienced on the floor, diagnose and correct problems in minutes. The rifle recycles through inspection. If it passes, it ships. If it fails again, it's scrapped for parts. This brutal quality discipline is what makes interchangeable parts work. You cannot allow even small variances to accumulate or eventually parts won't interchange. The Army receives rifles that function identically regardless of serial number. A soldier can grab any M1 from any crate, and it will shoot the same as any other M1. If his rifle breaks in combat, any part from any other M1 will fit and function immediately. No fitting, no adjustment. Just swap the part and return to the fight. This is the promise of the American system fulfilled at scale under wartime pressure. The workforce transformation is equally dramatic. In January 1941, Springfield employed roughly 3,000 workers. By January 1943, employment reaches 13,500. By peak production in 1944, over 14,000 people work at Springfield Armory. Where do these workers come from? Everywhere. Farm families from western Massachusetts, housewives from Springfield and Holyoke, African Americans migrating from the South seeking defense jobs, veterans too old or too injured for combat service, college students working between semesters. The women ordnance workers, dubbed WWIIs, fill 43% of production positions. They operate every machine, forging hammers, drill presses, milling machines, stock sanders, inspection stations, assembly positions. The idea that women can't handle heavy manufacturing work disappears within weeks of their arrival. A woman running 3 drill presses simultaneously while managing part flow proves just as capable as the man who previously held the job, often more so because she follows procedures exactly rather than improvising shortcuts that introduce variation. African American workers face more resistance but prove equally capable. Initially restricted to janitorial and materials handling positions, by 1943 they're operating production machinery, working inspection stations, and filling supervisory roles. Segregation in housing and some social facilities continues, but on the factory floor, capability matters more than color. If you can hit production quotas while maintaining quality, you keep your job. If you can't, you're replaced regardless of background. Training programs run continuously. New workers receive 1 week of classroom instruction covering basic shop safety, reading production drawings, using gauges, and understanding quality requirements. Then, 2 weeks on the factory floor working alongside experienced operators, learning the rhythm and techniques for their specific station. After 3 weeks, they're on their own, expected to meet production quotas that often seem impossible until muscle memory develops. Supervisors watch for workers who can't maintain pace. Some lack physical strength, others lack coordination or attention to detail. Those who can't cut it are moved to less demanding positions or dismissed. There's no shame in failure. The work is genuinely difficult, but there's no room for accommodation either. Production targets aren't optional. They're calculated based on military necessity. The Army needs X rifles per month. Springfield must deliver X rifles per month. Any shortfall means soldiers die. That brutal arithmetic drives decisions at every level. Sick? Come to work anyway unless you're hospitalized. Exhausted? Rest on Sunday and return Monday. Equipment breaks? Exit during lunch. No delays, no excuses. Just rifles flowing out the door at 90-second intervals. By May 1945, Germany surrenders. Production slows immediately. The Army no longer needs 3,000 rifles per day. They need maybe 500. Workers who've been running at maximum capacity for 3 years suddenly have breathing room. Some welcome the relief. Others feel lost. The intensity of wartime production created a culture where speed and volume were the only metrics that mattered. Peacetime production feels anticlimactic. Japan surrenders in September 1945. M1 production at Springfield ceases immediately. Contracts cancel. Workers receive layoff notices. By December, Springfield's workforce drops to under 3,000. Building 104, the facility designed for round-the-clock production, sits mostly silent. From 1937 to 1945, Springfield Armory produced 3,526,922 M1 rifles. Winchester produced an additional 513,880 under contract. Total M1 production during World War II, over 4 million rifles. Every American infantry soldier who landed at Normandy, every Marine who fought at Iwo Jima, every paratrooper who jumped into the Netherlands carried an M1 Garand. The rifle gave American forces a firepower advantage that shaped combat operations from North Africa to the Philippines. German soldiers, armed with Kar 98 bolt-action rifles, could fire perhaps 15 aimed shots per minute with perfect technique. An American soldier with an M1 could fire 30 aimed shots per minute, double the rate with equal or better accuracy. The tactical implications were profound. German infantry tactics assumed they could achieve local fire superiority through concentrated bolt-action rifle fire. This worked against British, French, and Soviet units armed with similar bolt-action weapons. It failed completely against American units armed with M1s. American infantry squads could generate rifle fire volume previously requiring machine guns. This forced German tactical adjustments. They increased machine gun allocation to infantry units. They emphasized close assault tactics to neutralize American firepower advantage. They developed the assault rifle concept specifically to counter the M1's semi-automatic fire. All of this because John Garand designed a rifle that could be manufactured at scale, and Springfield Armory figured out how to produce it every 90 seconds. The post-war years transform Springfield's mission. The facility shifts from production to research and development. Korean War in 1950 briefly restores production, but at much lower volumes. By 1957, the M14 rifle replaces the M1 as standard issue. Springfield produces the new weapon for several years, then production shifts, entirely to private contractors. In 1968, Secretary of Defense Robert McNamara closes Springfield Armory permanently. After 174 years of continuous operation, the facility that armed every American conflict from the Revolution through Vietnam shuts down. The reasoning is economic. Private contractors can manufacture weapons cheaper than government arsenals. Whether this is true remains debatable, but the decision is final. Building 104, the facility designed for M1 production, survives into the 21st century, converted to business space and educational facilities. Most of the production equipment is long gone, sold as scrap or relocated to museums. But the building itself stands as physical evidence of what systematic engineering can achieve under impossible pressure. The lesson Springfield Armory teaches extends far beyond rifle manufacturing. It's a lesson about the relationship between design and production. John Garand didn't just design a rifle. He designed a rifle that could be manufactured. He thought about tooling from the beginning, ensuring every part could be made on available equipment or equipment that could be practically developed. He prioritized tolerances that mattered and relaxed tolerances that didn't, understanding that excessive precision slows production without improving function. He designed for interchangeability at the system level, ensuring that parts fit specifications rather than individual rifles. This approach, design for manufacturability, is now standard practice in every industry. But in 1936, it was revolutionary thinking. Most weapons designers were craftsmen or theoreticians. They designed ideal weapons and left production problems to manufacturing engineers. Garand was both designer and manufacturing engineer. He understood that a perfect rifle you can't build loses every time to a good rifle you can mass produce. The transformation of Springfield Armory from 10 rifles per day to 164 per hour demonstrates another principle: systematic improvement through disciplined engineering. Building 104 didn't achieve peak production immediately. It took 3 years of continuous refinement, better fixtures, improved tooling, workflow optimization, worker training, quality systems. Every month brought incremental gains that compounded over time. This is the opposite of revolutionary innovation. It's evolutionary improvement guided by measurement and adjustment. The approach is less dramatic but more sustainable. By January 1944, Springfield wasn't just manufacturing rifles fast. They were manufacturing them systematically, with processes documented, workers trained, quality assured, and output predictable. That systematic capability is what won the Industrial War. The human transformation deserves equal recognition. 14,000 workers, many with no manufacturing experience, learned precision production in weeks because the system was designed for ordinary people achieving extraordinary output. This democratization of skilled work, making complex manufacturing accessible to non-specialists through intelligent tooling and training, prefigures modern manufacturing philosophy. You don't need craftsmen if your tools embed craftsmanship. The workforce demographic transformation, women and African Americans in skilled manufacturing roles, though partly reversed after the war, cracked open doors that would eventually open fully. Those women who ran drill presses and milling machines proved capability that undermined every argument about gender limitations in industrial work. Those African American workers who met production quotas and quality standards demonstrated skills that challenged racial stereotypes. The changes were incomplete and imperfect, but they were real, and they were permanent. The factory floor, unlike society outside, couldn't sustain discrimination once capability was demonstrated. John Garand retired from Springfield Armory in 1953 after 34 years of service. He received numerous honors: the Meritorious Civilian Service Award in 1941, the Medal for Merit in 1944, induction into the Army Ordnance Corps Hall of Fame in 1973. What he never received was royalties. He'd assigned all patent rights to the United States government in 1936. Over 6 million M1 rifles were eventually manufactured. Garand earned his civil service salary and nothing more. Congress considered a $100,000 grant in appreciation. The bill failed. Garand never complained publicly. He considered his service during the war sufficient reward. He died in Springfield, Massachusetts in 1974 at age 86, having spent 40 years in the town whose armory bore his rifle's designation. The M1 Garand's legacy extends into the 21st century. The rifle remains in limited use worldwide, still accurate, still reliable, still effective after 85 years. Military collectors prize original examples. Civilian shooters compete with M1s in national matches, maintaining skills and traditions from an earlier era. Museums preserve specimens alongside the machinery that manufactured them, tangible artifacts of industrial transformation. But the real legacy isn't hardware, it's methodology, the integration of design and manufacturing, the systematic approach to process improvement, the intelligent use of tooling to enable unskilled workers to produce precision parts, the understanding that wars are won by industrial capacity as much as military tactics. These lessons, learned through pressure and perfected through practice, informed every subsequent military production program. The Manhattan Project's approach to producing fissionable material used systematic manufacturing principles Springfield pioneered. The aerospace industry's production of jet aircraft in the 1950s copied Springfield's approach to managing complex assemblies. Modern semiconductor manufacturing, with its obsessive process control and statistical quality management, descends intellectually from the same principles that produced 164 rifles per hour in Building 104. The story of Springfield Armory and the M1 Garand is ultimately a story about transforming the impossible into the routine. In 1937, manufacturing precision rifles at automotive speed seemed impossible. Experts said so, production managers believed it, even some at Springfield doubted. But John Garand, the textile mill kid from Quebec who learned machinery by watching it run, who taught himself precision tool-making, who spent 20 years designing a rifle everyone said couldn't be mass-produced, knew better. He knew that impossible is often just a failure of imagination. That complexity can be systematized, that precision can be industrialized, that ordinary people given proper tools and training can achieve extraordinary output. He proved all of this by January 1944 when his rifle, machined to thousandths of an inch tolerance by workers who'd never touched firearms before the war, rolled off Springfield's production lines every 90 seconds. 164 rifles per hour, 3,936 rifles per day, 122,000 rifles that month. Enough firepower to arm 4 infantry divisions. Enough capability to change the tactical balance of World War II. Enough proof that systematic engineering defeats craft tradition every time scale matters. General Patton called the M1 the greatest battle implement ever devised. He was half right. The M1 was the greatest battle implement ever industrially manufactured at the exact moment it was desperately needed. The implement was brilliant. The manufacturing system that produced it was revolutionary, and both were the work of one engineer who understood that building it mattered as much as designing it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.